Let's get started. So welcome to the 10th lecture of Trustworthy Machine Learning. Good. So a few announcements. So exam date has been there so far, but now it's fixed. So the first exam will be on the 21st of February from 9 to 12 in the morning. And that's going to be in Morgenstelle. Okay. And there's a second exam, which was kind of written down on the web page before, but now the date is a little bit changed to 14th of April, now from noon to 3 p.m. Okay. At the same place. So those are the dates for the exams. And I was trying to learn about how to take registrations for the exams and so on. And apparently, I don't think there's need for registration officially. But I think I should still get some kind of list of people who wish to take the exam, right? So perhaps next week I'm going to collect this information from you, or probably no, maybe next week is the right time to do that. Yeah. Okay. Any questions for the exam or? Okay.
I have a question.
Sure.
There are no sample exams from past years because this is the
No.
direct
Yeah.
exam, right?
Yeah, but I'll try to give some guidance in the last lecture.
Okay.
For the exams. Okay. And today there's tutorial. So Michael said he's going to give a tutorial, and you can ask questions for the exercises. Okay. And let's get started for the actual material. So we are looking into evaluation metrics for the predictive uncertainty, right? And we've been talking about how to measure the correctness of your confidence estimate C of X. And we're talking about treating C of X as a predictive uncertainty, meaning that it should be a good representation of the likelihood of getting the answer right. But now we're going to take a look at C of X from a different angle as a non-predictive uncertainty. So what are types of possible non-predictive uncertainty, right? You can also think of C of X as a predictor for example, is the sample from out of distribution or not? That's not necessarily predictive uncertainty, right? Because even if the sample is from us out of distribution, you may still get the answer quite right, and vice versa, right? So in a sense, C of X is now OD detector in a sense. Or there can be questions like, yeah, is this sample severely corrupted or not? That's also kind of a binary detection task where the property that we are trying to predict corruption is related to predictive uncertainty, but not necessarily should be like aligned perfectly with the predictive uncertainty, like correctness of the prediction. Or there could be questions like, does this sample X admit multiple answers rather than just single answer, right? So to give you an example of OD detector point of view, you can write now this binary variable Y as whether this sample X is from outside of training distribution or not. Okay, and you can treat C of X as a feature for this binary prediction. And you expect Y equals to 1 for higher uncertainty values, right? And C of X should be a good estimator for in distribution cases, okay? So you can use the same evaluation metrics like area under precision recall or area under RC curve to measure the OD detection performance as well. Okay, so if you look at literature from OD detection or even general uncertainty estimation papers, you're also going to see OD detection performances in terms of this area under curve metrics. Likewise, this is much less popular, but you can also use the same C of X for as an estimator for multiplicity if the sample is accommodating more than one answers, okay, or if there is a severe corruption, for example. The same story here with different meanings. So that's the end of the summary evaluations. So we looked at predictive uncertainty, whether you're going to get the prediction right. We talked about proper scoring rules like log likelihood, Brier scores, or metrics like more sensible, like more intuitive metrics like calibration, expected calibration error, for example. And then there's weaker calibration metrics like ranking, area under curve, using different thresholds for the retrieval of correctly predicted samples. And now, if you only care about epistemic uncertainty, then probably it also makes sense to just look at OD detection performances. Or if you just care about aleatoric, then you might want to look at multiplicity or corruption detection. Okay. Now let's jump into methods. Okay. First, for quantifying epistemic uncertainty. Brief recap. Epistemic uncertainty means you're not sure because you have not experienced it before. So typically there are two possibilities. One, if the training data is way too small, or the training distribution is kind of not covering all the relevant regions in the input space. So there's some kind of underexplored areas eventually. In those kind of cases, there's a close connection with Bayesian machine learning. So actually this part of the lecture will be mostly Bayesian machine learning with a few other techniques other than Bayesian, okay? So the Bayesian way of saying, yeah, this space actually accommodates multiple possible solutions is through a distribution over the parameter space. So if the distribution is kind of wide, then that means you have huge uncertainty regarding what is the right model here, and so on. And this post area that is given after observing data points is, as you all know, it's product of prior term and some likelihood, the fit between your data points and your model, okay? So now let's look more deeply into the space of model parameters, because that's going to be the center of our attention for the next few slides. There are different names for parameters. You can write parameters or weights. Some people equate parameters with functions or models. Some people say hypotheses as well. And depending on which language you're using, you may use theta, W, or H. Yeah, I can't think of any other letter here, but yeah, these are typical choices. And you're kind of narrowing down the likelihood of your function from a prior, right, which is supposed to be wide. And then as you observe more and more data, you're kind of narrowing it down to post area. And hopefully your post area is containing the true model with high probability. Okay, so this is kind of the ideal visualization of what should be happening with Bayesian machine learning. Okay, right. From input space point of view, it's like you're adding more and more data here, right? And then eventually you're narrowing down the possible range of theta angles here, right? So that's what should be happening with Bayesian machine learning. So for this kind of analysis to happen, you need to kind of define the possible distributional format of your post area. In other words, what's going to be your distribution family of your post area? This distribution is, I don't know, you can probably call this mixture of Gaussian as well. which is supposed to be able to cover any kind of continuous distribution. If you allow as many modes you like, right? So the posterior can also be this generic and also highly multimodal, right? But also a lot of people like to use unimodal Gaussian distribution for the sake of simplicity of computation. Some people go for Dirac delta distributions, right? But in this case, they consider like sum of Diracs. Okay, so this is like semi-deterministic. Now you can all the way go down to deterministic Dirac delta function as your posterior. And then you now fall back to deterministic machine learning. So there's a whole spectrum of probabilistic, Bayesian machine learning, and deterministic machine learning. And depending on the parameter family you're choosing, you may also recover the original deterministic machine learning. So it's a generalization, basically. Okay. So if you have this probability distribution as posterior, then you can pretty much, express everything. It's a very flexible tool. Now, the way I like to think about Bayesian machine learning is you're basically training an infinite number of models at the same time. Deterministic model is training a single model at a time over the training set D, right? And you eventually get this theta star, which is a single model. And then what you do at test time is you use this model theta star to produce the output for the input of interest. Okay, that's it. Very simple. And that's what we have been doing. But with Bayesian machine learning, you're actually finding a distribution of models, like infinite number of models. And then what you do at test time is you average the predictions from each sample from this distribution. And then you get the sort of the voting from those infinite number of models. This is called Bayesian model averaging, okay, BMA in short. So what is a good example of that? So let's start with a simple example of that. So you can train an ensemble of models, and you can claim that this is Bayesian. In that case, you can think of your posterior distribution to be a sum of direct deltas. In this case, M direct deltas, right? So yeah, if you're not familiar with this Dirac notation, it means it takes infinity value when the argument is 0, and it's 0 when the argument is non-zero. Okay, so it's like a huge bump at one point. And if you integrate over this Dirac function or distribution, then you should get 1. Okay, so it's like a distribution as well. And now the idea is that you train M models by selecting M different random seeds. Okay, that's gonna put you at different locations in the parameter space. And because this is highly non-convex loss landscape, right? We're training. And therefore, depending on where you start, you're going to end up with different local minima. And therefore, you're going to get some kind of diverse set of models as a result. Okay, so the green here means random initialization. And by training, you will end up at different locations in this landscape. But if you think about random seeds in more detail, what they're actually controlling is more than just the starting points for the optimization. For example, if you change the random seed in PyTorch framework and also NumPy, what it changes is the formation of batches for samples for SGD. Because when you do sampling with this data loader, you're basically reshuffling the data set. And this is all dependent on the random seed you're choosing. Okay. And also, if you do data augmentation, most likely you're going to do that, right? So data augmentation has a lot of random components as well. And also, if you're using dropout or drop connect, drop stochastic depth, these kind of regularization techniques, then you're also going to use some randomness. So yeah, by choosing random seed, you're actually changing a lot of things. Now, yeah, you have trained M models, and what you do eventually is as follows. You do Bayesian model averaging, but now the posterior looks like a mixture of deltas. And one rule for delta distribution is that if you have integral and delta, where there's an argument that goes into the integral, and there's a minus some constant, then you can actually replace this delta inside the integral with the constant value that is subtracted. Okay, and so this summation, this delta goes away as a result, and so we don't have any integral here anymore, but the summation and averaging remains and goes outside, and you can replace this delta with these constants, which are theta amps. Sorry, theta is replaced with theta amps, and eventually what you get is average of the outputs from individual models. Okay. So this delta here is actually quite similar to the trick we used for multi-dimensional vector calculus, right? So in that case, the delta function was over discrete indices, and you can actually remove the summation and delta by replacing the indices in the summand. But in this case, it's more continuous version. So yeah, there are similarities, and that's probably why it's also called delta. Now to give you a bit more intuition of how this Bayesian model averaging is working, let's say we have the same kind of training data as before, like in the motivation figure. And let's say we have trained these three models here, theta 1, 2, 3. And let's consider this test data, purple X here. And we expect the outputs from all three models to be similar, right? Because this purple cross is at the same side, on the same side of the decision boundary for all the models here. And therefore, class triangle is predicted for all three models. And therefore, the BMA output will also be highly confident because all the predictions are agreeing. So maybe the max probability in this case is something like 99%. But now if we consider this purple cross here, then the models will give you divergent answers. For example, theta 1 will predict class red circle, but thetas 2 and 3 will predict blue triangles. And so if you average out the outputs for this sample, then you're going to get a mixture, something closer to 50%, let's say, okay? So that's, yes?
So when we average the outputs, we also average down separately for the confidence of each of the classes.
Yeah. Mm-hmm. So yeah, the y given x is like a vector for every model, and we are averaging the vectors. Mm-hmm. But then the argmax will be kind of different, and then if you after averaging, the max value will be more kind of smoothed out. Yes.
Question. P of y given x and d here is basically a categorical distribution.
Yeah.
Okay.
Mm-hmm. Yeah, should sum to 1. Yes.
So could we go back to the formula on the last slide and the model averaging? I haven't had the chance before. Maybe could we go through what the formula put on that Bayesian model averaging in general?
Yeah, here.
As well, right? So
yeah, this one here.
Maybe just in 1 minute talk through what we see there.
So this is we are assuming here that we have computed the posterior correctly, okay, which is theta given d. And now you have trained the whole distribution of models. And what you do is you are sampling from this posterior distribution, right? And for that sample, each sample is a model basically, right? And once you have this model, you can also compute the output of this model for input x. And that's given by this P of y given x here, given theta as well.
So the first thing is P of y given x and theta, that's the posterior.
Some people also call this posterior, but in this case, what I mean by posterior is the second term here for the model. Posterior for the parameter after observing the training data. So D here is training data and X is test data.
Okay.
Yeah.
So we sum over different, like we integrate over different sets of parameters. They are all a model and they're all weighted by the likelihood given the data we've seen.
Yeah.
And then we sort of weigh the excellent.
Exactly, yes. That's what's happening here. Okay. So I mean that's it for the ensembling, right? So now we try to take a look at whether that's actually working in practice. And here we have some results. So we are looking at classification error, NLL, log likelihood, and Breyer score. These are proper scoring rules. And now we have number of nets in your ensemble, right? So I didn't really go into all the details of ensemble plus R or ensemble plus AT or MC dropout. We're going to talk about that later on. But for ensemble, we see that as you add more and more models into the ensemble, you're actually decreasing the classification error. But this is not surprising at all, right? Because everyone is doing ensembling. Why? Because they wish to get better accuracies. So yeah, of course. But also in terms of the correctness of your predictive uncertainty, you're getting better in terms of NLL and Breyer score as you add more number of nets into the ensemble. Okay, so yeah, it seems to be working. So that was the MNIST results with a relatively small network. But also you can do this with other types of models like VGG or SVHN. And actually, this is quite scalable. So you can actually use ensembling for any type of model. Yeah, because you can simply train multiple models and average the outputs. Right, so yeah, if you exactly look at the spread of your output categorical distribution, you can measure the entropy to measure the spread, right? And if the entropy is 0, it means it's almost like a one-hot vector. And if entropy is high, then it's almost like a uniform vector. And in this case, MNIST is in distribution case. And you see that from the histogram, regardless of how many models you have in your ensemble, the confidence is super high anyways, very close to 0 entropy value. So the prediction is almost always one-hot vector. But now if you look at out of distribution case, if you're just using a single model, then you're actually getting very close to 0 entropy values, which is not good. But as you increase more and more members of the ensemble, you're actually increasing the entropy values for this OOD. So this is so ensembling is really playing a critical role here. Okay. Yeah, this is basically turning all these results into numbers. So as you increase more and more members in your ensemble, you're, yeah, of course, decreasing the error. Well, this is actually ImageNet. That's why I included here. And yeah, accuracy improves, but also the test log likelihood and Breyer score improves as well, which is good. It kind of shows that it's also working at an ImageNet scale. Yes?
When we use ensembles with prediction, the intuition is that single models with predictors make mistakes on different samples, make different mistakes. And that's why it average down the noise cancels out.
Yeah,
I
exactly.
would say that here the models are kind of sure about different things, and when we average them, that makes them unsure.
Yeah, exactly. Yeah. So I think what you said last is right, and right. So because if you look at individual models, right, like this single model case here, they're super sure about one of the classes, anyways, and that's not good. And only by averaging these out, you get higher entropy values, closer to uniform. So ensembling methods, pros and cons. It's conceptually simple, so it's good. You can just train m times and average the outputs. And you can use that for a wide range of models like linear regression or even to ChatGPT, the brand new model. This is also embarrassingly parallel. So once you have a lot of compute, then you can just train multiple models at the same time with different GPUs. That's it. Con is that this doesn't really feel like you're using the full potential of Bayesian machine learning. This is not exactly infinite number of models. And also from space-time complexity point of view, let's say you have only a limited number of GPUs, then you have to wait until the first model is trained and then train the next model and so on. And so this is not like scaling nicely. So the question is whether you can share some of the weights, for example, and also to expand the number of models that you include in this ensemble, for example, to infinite number. So let's look at one of the first work on expanding this number to infinity. Okay, so this is possible when the posterior is continuous. For example, like Gaussian. Okay, so we are assuming here that the posterior distribution is some form of Gaussian. So now this is a notation where it's a PDF notation, density function notation, where at value theta, and the parameters are mu and sigma. But I write down these stars here to indicate that you're eventually going to get the right values for mu and sigma by training on training data set D. Okay, so now instead of training theta directly, we are actually training mu and sigma with our training data. Okay, so theta is just a sample from this distribution. Okay, so there's a technique called Bayes by backprop. The starting point is the observation that, yeah, we can model the posterior with Gaussian, but it's not likely to be a Gaussian anyways, right? It's going to be much more complex. So what we can actually do is to minimize the distance between the true posterior and the Gaussian. So the figure looks like this. So this region is what the set of models that can be modeled by our Gaussian, and the true model is kind of lying outside of it. So what we can do is we try to minimize the distance between the posterior that we are going to get and the true model here as much as possible. So for measuring the distance between two distributions, KL divergence is the popular choice. So we do that here. And yeah, the formulation looks like this, but I'll go each line one by one. So we are interested in minimizing this term on the left. Okay. And the definition of KL divergence goes like this. So you have this normal distribution that you wish to find, and there's unknown posterior distribution. Okay. So, and you take P log P over Q. That's basically the definition of KL divergence for KL, P, and Q. And after this line, we right away apply Bayes' theorem on this posterior P of theta given D. Okay, so if you remember Bayes' theorem, what it says is you can swap A and B, but then you have to multiply the priors at the right positions. Okay, so in this case, P of theta given D is P of D given theta times P of theta over P of D. Okay, and then it's reciprocated here. So we have P of theta times P of D given theta. And then there's extra term, which is P of D only. But then that can be just taken out by the fact that it's independent of theta. So if you're integrating over theta, then you get 1, right? So there's only P of D term left here, but that's kind of constant because here what we are trying to optimize for is mu and sigma. So we just treat that as a constant term here, C, okay? And now you can expand the logarithm as follows, right? So, right, this P of D given theta is kind of separated out here and also reciprocated, and there's a minus in front. Okay, and now we recognize that the first term is, again, KL divergence. And this time we go back to the KL kind of notation. And the second term now is a cross-entropy term between two distributions, right? So this is basically, these are two different ways of writing an expectation. So you can think of this integral here as an expectation over theta, where theta is sampled from this normal distribution, okay? And then there's C. And you can also expand this data term, likelihood term, by observing the fact that all the samples are independently drawn from the distribution. And therefore, you can write down the joint probability as the product of individual probabilities. But then now the individual probabilities can also be written in terms of P of y given x and P of x, okay? And now P of x given theta is treated as a constant, which is something that our model is not modeling, right? So that is written as C prime here. And we are left with this P of y given x term here. And that goes into logarithm, and therefore the product here becomes a summation. And yeah, there is actually also 1 over n here. And that, when taken out of logarithm, that becomes 1 over n. And there's a C prime term, which is subsumed into this C term here, okay? Okay, so that was, that's very close to our eventual formulation. So the last step is to turn this expectation via Monte Carlo estimation. So instead of trying to compute this exact value, we try to just sample from this Gaussian distribution and compute this output here, okay? And that's a close enough approximation of the expectation. In fact, we go even more crazy here and actually usually take large K equal to 1 when you train models. But that's probably fine because we are kind of averaging across different iterations of the gradient descent. Yeah, we're doing SGD anyways. Why not introduce a few more approximations of the expectations anyways? Okay. So that's what we do. And yeah, it's already kind of convenient format, but we also try to make it more deep learning friendly, okay? So now first the KL term. We have the full freedom to choose the prior for this KL term. So a popular choice is standard normal. Why do we have a full freedom, right? Because we only need to encode our belief through our prior. So yeah. And also it is very likely that, you know, in parameter space, there's a lot of similarities and symmetries, and therefore the solution is like spread across the entire space. So regardless of which part of the space you choose, it's very likely that you're also going to find the solution anyways. So yeah, that kind of justifies the choice of standard normal for your prior. And why don't we restrict our attention to Gaussians as posteriors, but only with diagonal covariance matrices. If you actually allow for full covariance matrices with full degrees of freedom, then you run into a lot of problems computationally. So that's computationally easy to just consider diagonals here. And then if you, there's an analytical solution for your KL divergence between two Gaussians, which goes like this. So here, mu and sigma are the parameters that we are learning eventually. Yeah. Okay.
Sorry, can you
Sure.
back to the full, sorry, to the full.
Sure.
The I think I get lost in the weeds with all this detail. What's the KL versions at the top again?
So that is the objective that we wanted to minimize because we believe the true model is kind of outside of your the set of things that your prior can posterior can handle.
Posterior and the last one.
So yeah, this one is posterior, right? And this is the network that you're trying to train. And the aim is to make sure that your network, which is encoded by this Gaussian distribution, is as close as possible to the true posterior. And of course, training this is impossible because we don't know what the true posterior is. And so without having to understand what true posterior really is, we go through very conceptual steps here to reach something that is actually computable. And we justify using that equation by saying, yeah, actually, if you train with this objective, you're actually training with this original objective.
Yeah.
Okay. Yeah.
So we never try to specify what PP is.
No. Yeah. That's the trick. That's very complicated in a sense. But also, I'm gonna say like, yeah, these are like conceptual steps where we try to justify what we're doing, but also from practical point of view and also very intuitive standpoint, this equation makes sense on its own as well. So that's what I'm kind of also trying to show here. Okay, but before that, I'm going to talk about how to make this deep learning friendly first, right? So the first term is just a differentiable loss function for mu and sigma. So this is DNN friendly. But now the second term is not exactly DNN friendly yet because there are two parameters, mu and sigma, that we wish to train. But the loss function is not depending on mu and sigma in a straightforward way. You first have to sample from this distribution encoded by mu and sigma, and then that parameter is used for computing the loss, right? So how do you kind of differentiate through all these non-trivial layers, right? And that's where the reparameterization trick comes in. So you can think of this sample theta as a procedure where you first compute mu, or first get mu from somewhere, and then you also get sigma from somewhere, and you multiply a standard normal with this sigma pointwise, because sigma is diagonal, right? So it's multidimensional, and then sum it. And then it has the same effect as sampling theta from the distribution encoded by mu and sigma. Okay, so you can kind of separate the parameters mu and sigma from the sampling operation, right? By sampling from this non-parametric, or yeah, this is parametric, but there's no trainable parameter inside this epsilon, right? So sampling can be kind of separated from the parameters in this case.
So the idea is we sampling operation is not differentiable, so we can't back up.
Exactly, yeah.
And but where do mu and sigma come from now?
So these are like model weights. So they are like, in PyTorch point of view, these are NN dot parameters. So you initialize them and you train over iterations. Okay. And there is one less important but still interesting trick, which is that sigma should actually be always positive in this case, right? Because these are variances. And how we do that is by instead parameterizing another real value, which is allowed to be also negative, rho, and then you apply an operation which makes sure that the output is positive. This is called soft plus, and this is just log of 1 plus exponential of the value, and it ensures that the output is always positive. Yeah, all the operations are element-wise. Okay. Sure.
I suppose you would also usually have a hyperparameter to balance the two parts of the sum. Usually.
Yeah, you can also do it, but yeah, you can also do it. But to make it simple, I just removed all the hyperparameters here. Yeah, but that also matters. Yeah. So if you actually look at the actual soft plus function on PyTorch, you're also going to find those hyperparameters, I think. Yeah. So this is an example PyTorch code for base by backprop. This is just a linear layer, but I also kind of put a loss function on top. Okay, so in the init phase, you define the parameters, right? So mu and rho are now parameters, okay, of size the same as the number of weights in your model. And now during the forward pass, you get an input to this linear layer. And the first thing you do is to sample from this standard normal, right? And then you compute sigma from rho by applying soft plus, okay? And then you multiply epsilon with sigma and then add with mu. And this whole operation is differentiable with respect to rho and mu, okay? And now you do matrix multiplication between x and theta here. Now, in terms of computing loss, we realized that you're actually just taking one sample per iteration, because you didn't actually take multiple samples of theta here, but just single theta here. And the output is, you can think of this logit here as the output of this torch.mm, right, the Ford. And these are fed into cross entropy, and you just compare against the target labels. It's the same thing as when you train classifier in general. And then you get log likelihood, more precisely negative log likelihood. And again, here you need to compute this KL regularization term, which looks like this when you write that down into PyTorch code. It looks like that. Yeah, and here again, you need to compute sigma out of rho, and use some the KL term and the log likelihood term as the final loss function. That's it. You just train this with backpropagation, SGD. So that was the trick in general for training an infinite number of models. The first step is you can do some kind of variational approximation, and then that is mainly to justify what you're doing, right? And then eventually what you came up with is some kind of combination of KL term against the prior and some likelihood term for training the model, actual model. And as for the likelihood, this term, second term here, what you're doing is you're sampling this parameter from these infinite possibilities of models at every iteration, and make sure that your gradient flows through this parameter all the way down to the actual component parameters of the posterior distribution. And this is basically the secret sauce for training multiple models at once, while sharing a lot of weights and saving computation. And for making sure that the gradient flows through this sampling step, you use reparameterization trick. Yeah, if there's a need to clip parameter values, then you can use soft+, or you can also use ReLU if you like. Yeah, that's it. Any question? Sure.
This looks like a slightly general version of what happens in a variational autoencoder.
Yeah, it is.
It's really put my head around what is exactly different here.
So for variational autoencoders, so these are called variational because you have some unobserved variable. So in this case, the unobserved variable is theta. We do not have theta as a training sample or anything, right? For variational autoencoders, we have the intermediate latent value z as unknown variable, right? Having set what is the unknown, the rest of it is the same. You try to estimate the posterior for this unknown given training data, and then you build some kind of KL distance between your posterior and the approximation of that posterior, and you get the lower bound or upper bound depending on the sign. And eventually you end up with some KL term against the prior for this latent and some data term for training the parameters of the approximation. So it's the same thing with different variables.
Maybe then just a simple question. If it's the same thing, is that how we call the like the unknown, this latent variable? Why did these people have to write a whole paper and not just say, okay, if we use this Z to represent the model weights, then it's Bayesian uncertainty and like how is it different? Why like get a step in the conference of a new idea?
I think it's quite interesting still you still see a lot of papers around variational approximations in different contexts. I don't know, to make an analogy, I think it's almost like saying, yeah, you can train a DNN for some problem, right? It's the same story otherwise. I think the other critical difference is that you're now dealing with the parameters that you have to train. But in a VAE case, you're not actually training parameters, but these are like intermediate outputs. And the parameters are kind of separate from that. Yeah, to make some difference, to find some, yes.
I think that maybe it was just concurrent work, not exactly sure when VAE was published, but I think it was either 2015 as well or 1 year earlier. So
yeah, I think it was 1 year earlier. I was wondering about that, and I checked the citations for this paper, and they were actually citing this VAE paper as well. Yeah. Yeah.
So I'm not yet convinced why this is better than just taking ensembles, because it seems to me that this prior assumption is very restricting our subsurgation, and also our posterior estimation is also very restricted because we're also restricting our subsurgation. So in ensembles, we don't have to really think about a correct way of choosing the prior, and the models can differ in whatever ways they want to. In limit, it's a close estimate of what would be the true posterior. So why is this better?
So there are pros and cons. So what is the pro for this? I can think of one pro, which is you can also think of a confidence interval for the posterior, for example, in such a high dimensional space still, but it's probably going to be meaningful to make sure that certain area around mu is always a solution. And you're sure that around some region defined by your Gaussian, your sigma, you're likely to get a valid solution. So if you care about like getting a region in the parameter space where it's where everything is a solution, then I think this has more edge. But I agree with the rest of it. Like I do think this is not a better solution than ensemble method in general. Yeah. Okay, so let's probably take a 5-minute break here and resume. Resume recording works. Okay. Good. So we looked into how we train this infinite set of models. Now, the question is, how do we do inference? By the way, it's the same story. So after training this objective, what you end up with is mu and sigma for your Gaussian, right? And then you're computing the Bayesian model averaging then based on this learned mu star and sigma star, okay? And you're approximating that by sampling k times from this this normal distribution. And that's it. You average the outputs from this. So yeah, I'm kind of reiterating a bit, but so the ingredient here for training infinite number of models is you sample and then train that model with likelihood, and then eventually you are trusting this model to represent a good set of plausible models that is working well for the training data. So there are multiple solutions in this set. And if the models disagree here again, then for that sample, it is likely that the uncertainty is pretty high and it's out of distribution. Yes?
So this, in some sense, is not more Bayesian than the previous approach. It's just that we find the places where to put those sum of Dirac functions in a principal way, using the objective which we use.
It's kind of a different way of modeling posterior, I would say, right?
Is it a different? Because the previous slide looks like as if we're again having in the end just an average, as if
so here the
samples from normal distribution will look like as if it was a sum of a Dirac.
Yeah, so eventually computationally saying, I think the test time is exactly the same, right? But the underlying conceptual meaning is kind of different, because now here, what it's saying is all these models within this Gaussian make sense. This is a big statement because then if you sample from any of those, it's also like locally, this ball has all the dimensions of the parameter space, right? So this is a huge volume compared to the ensembles, which are basically points around the space. So this is a very nice kind of small region in the parameter space, and you're sampling just k points because you are kind of limited by computational power and so on, and probably you don't really gain much from sampling too many more, right? So yeah, eventually the same, but the training procedure and the meaning of the space is kind of a little bit different. Okay, but this also sounds familiar to some people before, right? Saying, yeah, we have been using dropout for several years. And if you think about dropout, you're actually sampling the weights every time, for every iteration. So this is how dropout looks like after dropping some of the connections, right? So every time you're training the network with different connections. So if you write it down, what you're actually training with dropout looks like this. So it's the same cross entropy loss function over all the training data, but now at random you're sampling from this Bernoulli distribution with probability p, and yeah, you're multiplying pointwise, multiplying that with the weights, and then get the output. So this looks very similar to this formulation we had right here. So some people said, yeah, this is Bayesian. Yeah. Right. And what you do during training is you do dropout as usual. But what you're changing is just the test time. You do Bayesian model averaging across different instances of Bernoulli choices of the weights, and then average them. And here, I think the author of this paper also trained P in some way to get the more precise distribution. But in practice, you just set it to, I don't know, 0.5 or something like that. But you don't, you have seen that it doesn't work well in practice, actually. I said, I'm going to talk about it later, right? So this is the curve for MC dropout. It's not as good as taking ensembles, okay? Yeah, and there are also a lot of people complaining about MC dropout, and these days, this is treated as something that doesn't really work in general, okay? And I brought some videos, and we are kind of transitioning to the next topic, basically. And I really like those loss landscape visualizations. It's quite amazing. When I talk about Bayesian machine learning, loss landscape, I always imagine this kind of nice visualization in my head. So I thought it's going to be nice to kind of share this visualization in our heads. Okay. Yeah, it's amazing. So that's basically, yeah, starting again. Another video. Yeah, the same message, I guess. Yeah, you're kind of following this landscape to local minima. Okay. Anyways, so based on that, can you think of creative new ways to train infinite number of models? Maybe yes. I'm going to give an answer. So we're talking about like training a Gaussian space around the point. But we can also think of training more global kind of connections between two faraway points in the parameter space. For example, a curve in the parameter space. And here the color, so X and Y indicate two selected axes from parameter space. And the colors mean the training set loss value. So you see that along the curve, the loss is always very low, meaning that perhaps all the points along the curve is a valid solution for the training set. Okay, so we are already seeing a good example of an infinite set of models here. So how do you train such a curve? I'm trying to argue that this is also Bayesian, because you're now training an infinite number of models. It's the same story. So you first model a curve as a parametric distribution over a high-dimensional space. And every iteration during training, you're sampling from this curve, 1 point from the curve at a time. And then you use the reparameterization trick to separate the randomness of this choice and the back propagation to the parameters describing this curve. So the first question is, how do you parameterize such a curve? So the starting point is you basically have to train two models in the first place by, I don't know, randomly initializing them and so on. And you fix them throughout. So these are constants. And now you try to look for a third point, phi, which is trained now. And now the line segment connecting theta1 and phi and theta2 are are supposed to be the solution set for your loss function. And yeah, this is the equation for parameterizing your line segments from t0 to t0.5, which is phi, and t1 means theta2. Okay, so if you plug in t equals 0, then you're going to get theta1 here. T equals to 0.5, then you're going to get phi, same here. And then if t is 1, then you're going to get theta2 here. Okay. So based on the parameterization, you can parameterize the sort of distribution over this line segment using uniform distribution. You first sample from this uniform distribution over t between 0 and 1, and then you apply this curve formula, right? And then each point on this t will be translated to a parameter along this curve, okay? And this procedure is differentiable after selecting t, right? So again, the sampling operation for t and the actual parameter, these are well separated, and therefore we can use reparameterization tree. Well, this is basically reparameterization tree. And so by training through theta, we can train phi here and find the optimal phi that's giving you the right solutions for every point on the line segments. So this is how the objective looks like. So like before, we try to minimize the parameter for your distribution such that whenever you sample from this distribution, the loss should be low, right? Very low. And you can use a reparameterization trick to write this down in the following way. You sample from t, and then you compute this theta phi of t based on this formulation. So if t is between this, you compute this linear equation. Yeah, so this is linear with respect to phi, so everything is differentiable. Nice. So when you train such phi, then this is what you eventually get. So yeah, so and this is kind of showing you the training loss value. Nice. And how do you do inference? It's the same story. So you just sample from t again, and then get multiple values of phi, theta phi along the curve, and then average the outputs. You can also just choose equidistance points along the curve as well, if you want. And here the basic, the central point of this paper is that you should be surprised because whenever I choose arbitrary 2 points that are solutions in the parameter space, it is almost always possible to find the third point, which is parameterizing a solution curve that's connecting these two solutions. So that means all the solutions in the deep learning landscape are connected to each other, at least with some kind of curve, which is fairly simple, right? These are not like straight lines, but if you go if you have one extra point in the space, then you can connect them via two line segments, which is quite surprising.
So that's actually one of the cases where there's the visualizations in 2D parameter space give a bad intuition on how things actually work in high dimension.
Yeah, so there are millions of parameters, so it's actually not a big surprise either, because if there are millions of possibilities, then probably one of them should be working the right way, right? So this is another fancy visualization of mode connectivity. So you have two solutions here, and it's possible to connect these two solutions with some curve in the space. Yes?
What are we exactly saying about this curve? What are the constraints? Do all the points on this curve have some kind of a loss not larger than some kind of threshold? Or
So
what is exactly surprising about this?
Yeah, from the thresholding point of view, I think you can set something like 0.1 as the loss value, and it's surprising that the loss value is kind of lower than 0.1 throughout. And in terms of maybe the classification accuracy, which is probably more intuitive, it's like more than, I mean, it does not lose much from the independently trained points, for example. And this is what is probably surprising is that the neural network has a huge capacity to actually accommodate an infinite number of solutions globally rather than around a certain point. We have shown that it's possible to train an infinite set of models around a certain point locally with the Gaussian posterior, right? But here we are kind of expanding that to global traversing of the parameter space. And well, this was probably the first work showing this is actually possible. Okay. Right, so actually this is one of my papers. I used the same technique of connecting two different solutions in the parameter space. And I would like to call this further surprise because it's what we show is that even for heterogeneous pairs, θ1 and θ2, it's also possible to connect them with some curve. What I mean by heterogeneous pair here is that two solutions that are biased to different attributes. Okay, so one solution here is biased to color. So this model is solving the problem using color features. And this model here is solving the problem using orientation feature. Okay, and we kind of devised the training data in such a way that using either color or orientation can give you a low loss value, right? So it's kind of yeah, all these cues are okay, right? But now it's also possible to connect these two solutions with a set of solutions as well. And here, what is shown for this leftmost figure is the loss value for the training data, right? But of course, you would probably wish to also measure the performance of the solutions according to different cues. So the right two figures are the loss values for unbiased test sets, where we have samples where if you're looking at orientation cue, then you're going to get high loss value and low loss value for color cue, and the other way around for this one here, right? So we can kind of see that, yeah, there is a transition happening from color bias solution here to orientation bias solution here. Okay, so there does exist some kind of transition in the middle, but it's surprising still that those two very different types of solutions can also be connected. And also it's nice to kind of see that the space of solutions occupied by color bias solution is much greater than the space of solutions for orientation, for example. And that probably explains why if you just train a model, then it's more likely to get a color bias solution than solutions that are biased to other types of attributes. Okay, so this is more volumetric point of view for explaining why color is more favors bias for the model than the other cues. Right, so that was it for training a set of models. Yeah.
I don't think I fully understood. What are the axes? Are just like indicators for parameters, I guess?
Right. So the starting point is two models, right? And we are basically training a third model, right? And when we have 3 points in millions of dimensions, we can still pick out 2 dimensions where we can put all 3 points in the same plane, right? Yeah. So this is exactly that plane where we see those 3 solutions together. And of course, we have like million minus 2 other dimensions which are hidden here. But yeah.
And the 2 plots on the right, can you explain again what we're seeing there? So we're testing both models, like we're testing the set of parameters we're seeing on different tasks, like predicting color and predicting orientation.
Yes, yeah.
But
with different training data.
Never trained on
yeah.
We're using the model to do something that
So what is a good example of that? So let's say there's a strong correlation between my favorite example, frogs and swamps, right? So this is the loss when the training samples are always from swamps, right? The frogs are always from swamps. But now, let's say your model is looking at the background, right? And color is like a background here. And here you're still testing on the case where only the background makes sense, right? And so if you are actually looking at foreground, then you're not solving the problem.
So there are no frogs.
There are no frogs, yeah. And vice versa here. Okay. Yeah. So the training, the data set is kind of shifting in all 3 scenarios. Data set is encoded by the loss function, not the space. So the space is the same. The only difference is the loss function. And if you think about loss function, well, loss function is basically data set. So here, only the data sets are changing. Yeah. Okay. Now we can also look for other cheap sources of Bayesian machine learning. So if you look at how SGD is really trained, as the training epoch goes, eventually you're going to reduce the learning rate, and your solutions are kind of not moving too much around certain point in space. And we can treat those set of points towards the end of your training as samples from some Gaussian. Okay. That's it. That's the idea behind this SWAG, stochastic weight averaging. So SGD is already trained with noises, right? So in a sense, you're kind of sampling from some unknown distribution during training. And therefore, at the end of your training, you can treat those iterations as some kind of samples from the final posterior of your parameters. This is also very similar to MCMC point of view, Monte Carlo Markov chain. And I think the first paper which kind of started this MCMC point of view is stochastic gradient Langevin dynamics paper, which was way before than this paper. But kind of, to me, the intuition is the same. You're training with some kind of noise during training, right? So eventually, towards the end of the training, the iterations are kind of encoding samples from some kind of distribution. So in this parameter space, you are looking at trajectories for the last few iterations. And based on the mean and variance of those trajectory samples, you can infer what is the Gaussian from which those points are sampled. Okay. So in a sense, again, you're approximating your posterior with some Gaussian. But now we are not going to use variational approximation to get those Gaussians. We'll go even simpler and use those last iteration weights to estimate the mu, right? We just average them. And the diagonal is like a sample covariance matrix. we're actually just looking at the diagonal components in this case as well. So you take the element-wise square of all the thetas and subtract the square of mean from that. And that's going to be your sigma squared for every dimension. And this is called swag diag. Yeah, swag is stochastic weight averaging Gaussian. And they also introduced swag, which is using full covariance matrix as well. But that's obviously more complicated. And yeah, I don't see much point in like talking about full covariance matrix here. I think what's important is to get the right intuition of what they are doing. And this is, of course, highly scalable. You don't even need to train M different models here. You just need to train the model as you have been doing, and just take the few iteration samples from the last training epochs. Yes?
Do we average over last M training epochs, or what is it that we averaging over?
We are averaging over, yeah, last M, yeah, last M epochs. Yeah, where M is some kind of hyperparameter, I guess.
This is really easy. Like that seems like something we can do all the time.
Yeah,
Like
yeah.
automatically implement and improve.
Yeah, that's their point, right? Yeah. You can do that for ImageNet. And also, I think you can even do that for any other type of models like ChatGPT, even. I don't know. So here you're comparing the normal SGD, right? And this SGLD is stochastic gradient longevity dynamics, another type of MCMC method. Oh, this is not shown actually. I just cropped it from somewhere, so probably this was cropped out. SWAG is full covariance matrix, and SWAG diag is a simpler one. So I think, okay, now this is confidence minus accuracy for different confidence values. So they are actually trying to measure this, some sort of ECE right here, where instead of showing accuracy versus confidence, they are showing the difference at different confidence levels. So closer to 0 is good. And it looks like SWAG is better than SWAG diag, right? While SWAG diag is kind of similar to SGD, which is too bad. Yeah, but the point is that this is done on ImageNet. So it's for free and scalable. So now, quick wrap up for Bayesian approaches in general. They look principled, but as we have been kind of discussing through Q&A as well, they depend a lot upon the assumptions that are hardly true. So first of all, you need to have some sensible prior, such that your learning is not infeasible or inefficient. The learning could be infeasible if the true model is not supported by your prior, or if your model is only supported by a very thin tail, then your model learning will be inefficient to find the true posterior. And also our assumptions over the actual family of posterior distribution should be correct ideally, but it's not going to be Gaussian, right? So yeah. And also we are working with high dimensional spaces, like millions of billions parameters. These are making these assumptions even more difficult. Yeah, because for example, yeah, to make sure that your posterior estimation is correct, you need a lot of samples, especially for complex distributions. And if it's a complex distribution in a high dimensional space, then you need like exponentially many number of samples to check this. And this is not really feasible for deep learning, right? Okay, so now let's look at non-Bayesian approaches for epistemic uncertainty. So what is the requirement for epistemic uncertainty in the first place? The confidence value has to be low when the data is kind of away from seen examples, right? And to have that kind of property, we don't actually even need an infinite number of models to do that, for example. One possible alternative is to measure the distance between test sample and the training samples. That's probably simpler, right? So one simple way to measure closeness to the training samples is by measuring the closeness to one of the classes. And here, all the distances are kind of measured in the feature space, the penultimate layer of the neural network, which is right before the linear classification layer, okay? And here, C encodes 1, 2, 3, like the classes here, right? The color is class. And let's say your test input is this cross here, which is very close to the training samples for class 1. Yeah, we can say this is in distribution because this is close to one of the clusters. And now this sample can be determined to be out of distribution based on the fact that it's not close to any of the classes. So how can you measure the distance to different clusters? We first compute all the features for the training set and compute the mean vector for every class here and compute the covariance matrix for every class. Okay, like this. And then you have some kind of Gaussian around each centroid, class centroid. You can also tie the covariance matrix. That's what they actually do in this paper, I guess, to simplify computations. So you can just take the average of all the covariance matrices. But this is kind of a weighted average because every class has different samples. So it's proportional to the number of samples in each class. And yeah, that's your covariance matrix in general. And now we define a distance between a test sample and a class C by Mahalanobis distance. It's very close to log likelihood of that sample given given class distribution here. Right, this is very similar to the formulation of PDF for the Gaussian, right? So that's one point of view. The other point of view is you're basically taking L2 distance, but you're weighting every dimension of the L2 distance by this covariance matrix, such that if, let's say this is a long Gaussian, like looking like this, then distances to the narrow direction is further weighted, and distance along the long Gaussian direction, long axis, is down weighted. So it's like likelihood again. Okay, and the final confidence measure is given by, yeah, I kind of regretted using C for class here because there's kind of clash of, yeah, confidence and class. But I checked the slides again and I realized, okay, probably this is all right, given that we do not really talk about confidence and class together very often. So yeah, please read this according to the context. Okay, so we just take the minimal distance between any class and this sample, and then take minus of that because we are interested in confidence. So the closer the distance is, the confidence should be higher, okay? So that's your confidence, and that's it. And then those people measure the OD detection performances, for example. this AUROC metric we talked about, right? So compared to max probability, performance of detecting OD, Mahalanobis distance is doing a better job here. Yeah, but these are just for just examples. I'm not trying to say that Mahalanobis distance is always better than max probability. This is just for this particular setup, and there's no guarantee. And yeah, as before, there are also metrics like AUROC that they measure. And here they're comparing baseline, which is max probability, ODIN, which is another method that I'm not going to talk about in this lecture. There's Mahalanobis theirs, and they compare those performances in different situations when your in distribution is CIFAR, SVHN, and so on, and the OD distribution is different from the in distribution. So for those kind of evaluations, you need to have a good set of in distribution models and a diverse set of OD distribution models. Okay, data sets, sorry. So that was one example of using distance. The other example is using RBF Connell. It's actually very similar. So again, you measure the class centroid for every class, and then take the L2 distance. And then you take exponential of that and take minus and yeah, divide by some sigma. And this is actually quite similar to Mahalanobis distance. But here you're just taking likelihood of that sample given some class Gaussian distribution. But here, one nicer property than Mahalanobis distance is that this is nicely confined to 0-1 range, okay? So in other words, you have some nice interpretation of this number as some probability. If anything is between 0 and 1, you can treat that as a probability. And we can define the confidence level similarly as before. So we take the max kernel value against all the other classes. Yeah. So yeah, this is nice property. So we can apply proper scoring rule for this criterion as well, again. Okay. So now another exercise for turning proper scoring rule into some kind of loss value, loss function. So we apply the log probability scoring rule for this max RBF similarity confidence value, right? C of x, which is given by max over the classes for all the kernel values. And this is the case when your prediction is right. And minus log of 1 minus confidence value when your prediction is wrong. So this is your proper scoring rule. And I wrote this down as a minimization problem. So lower is better in this case, actually. Okay. And so what do I mean by this notation here? So YC here is one-hot vector for the ground truth class. So YC is YC is 1 when C is equal to the ground truth label and 0 otherwise. Okay, so this means your argmax of your K is equal to the ground truth. The aim here is to upper bound this minimization objective with a familiar loss function binary cross entropy. Okay. So we make a series of observations here. So if this prediction is correct, the argmax value for K is correct, then we may write the first term minus log max K as summation over YC log KC. Why is that? Because YC is a one-hot vector. So this summation can be written as log of K with some index where the index is corresponding to the case where YC is 1. And we said that YC is 1 only when argmax, it's 1 at argmax, right? And yeah, that's exactly the value of max K C, right? I hope it's clear. And so we can write this down as this summation, right? So the first term is kind of written in some form that looks more like BCE. And now for the second term, which was minus log of 1 minus max K, this can be, you can basically take out this max operation all the way outside, because you are kind of flipping the sign twice, and log is a monotonic function. And now when your prediction is wrong, you can actually bound this max of minus log 1 minus K by the summation over many minus log 1 minus KC values, because the point where this is maximized, the index where this value is maximized, corresponds to the case when YC is 0. Why is that? Because KC is maximized when YC is 0, because you're not predicting the right answer here, right? So this max value here is subsumed in one of the summands here, and therefore the summation is bounding this max value, okay? And you can rewrite this summation as the summation over the whole C values, but you're adding this factor in the front. This is like different way of writing this down. So this value here is 0 only when YC is equal to 1, which happens only once, okay? So in other words, you can bound your proper scoring with those following two expressions. And if you're actually summing these two together, then this bound holds for any situation, whether your prediction is right or wrong, you're still bounded by this this summation, okay? And we define this summation as your loss function, and we realize that this is actually a binary cross entropy loss function, okay? And this formally advocates the use of this form of binary cross entropy function for training the whole network using this RBF corner. And this is exactly the loss function they use for training the model. Okay. Okay. And there's one more trick they used. So they're making use of the class centroids, right? Because for computing K, they needed to compute the distance between every sample to the corresponding class centroid. And if you think about class centroids, they're actually moving across training iterations. And so if you're computing your centroid every time you have a new batch of samples, then that's going to be very flaky. And what they do is they take the moving average of those centroids over iterations to make it more stable. So, and also the number of samples per class for every mini batch changes over iterations. So they also keep track of the number of samples for each class over iterations, right? So NC, small NC is the actual size of class C in the mini batch, and large NC is kind of the moving average. And MC here is the feature, the mean average feature location for that class, okay? So you're taking the average here. No, actually you're taking sum here, and then you're taking the moving average of the summation. And eventually for every iteration, you're dividing your MC by NC to get the average location of your centroid. And typically you give gamma value between 99% to 99.9% to make it stable, okay? And now if you do that, there are some results showing, yeah, if you have in distribution, which is cipher 10, and out of distribution, they tend to have different kernel distances. And therefore, it's a good indicator of how to separate these the out of distribution from in distribution cases. In terms of numbers, this is quantified in area under curve. And DUQ is the quantification using this RBF kernel. Log likelihood ratio is another method that I'm not going to talk about in this lecture. Single model means you're using this C of X here, which is max RBF value, but you're training the whole network with softmax cross entropy. And there are some ensemble methods as well, and Mahalanobis distance they compare against. And their point is that their method, after training with the objective that I talked about, is giving a good results. Okay. Yeah, so actually that's it for today, and I'm going to resume from this point next week. Thanks.